All right, welcome back to Algeblocks. Today we're going to be looking at subtraction. Subtraction is also an operation, and it also corresponds to a particular action on the Algeblocks, on the mat. So remember, addition was placing, well, subtraction is removing. At the beginning, there's no other interpretation of subtraction. It's not shifting to the other side. It's only removing. Now that's often a hard thing to do, having come from the add the opposite world and having practiced that a lot. So we're going to try and resist using add the opposite as much as possible until we can actually prove that adding or removing is the same as adding the opposite, which isn't actually trivial, and it isn't really clear to kids why that's the case, and often they just take it as faith. So let's look at page 10, and we're going to model a 3 minus 2. So just like we did with addition, we're going to start. We're going to have the operation of removal and then the change. So we need to start with 3 and then remove 2. So we're going to, if we're lucky, start with 3. And what we need to do to subtract 2 is take 2 and remove them. So what we're left with is 1. So that removal, that process of removal, was actually the subtraction. So if I move them back, and I say we're going to remove, that removal is subtraction. In Algeblocks, subtraction is always taking that change off the mat. No other interpretation. So let's take a look at another example. So that one was pretty straightforward, as it is in elementary school, where this happens fairly easily, but fairly early. But now, if we have 3 minus 5, we're going to be removing 5. We're starting with 3, and our change is 5. So let's try that. All right, going to be starting with positive 3. All right, and we need to take away, actually remove from the mat, 5, positive 5. We need to remove positive 5. I don't see the positive 5 that I could remove. I see 3, but I don't see positive 5 to remove. And the only thing I can do when I'm modeling that subtraction is to remove. Now, I guess we're either stuck or we need to look at 3 in a different way. Is there another way that we could represent 3? Think back to some of the early stuff that we did on Algeblocks. Well, we always have the option of 0 pairs. If you remember, this is also 3. Now from this I could remove 4, but I couldn't remove 5. But we're getting closer. What if I do... Oops. Oh, come on. What if I do this 3? Is that still 3? It is that the starting mat is still 3, although it looks a little funny because we have some 0 pairs. But look at what happens now. In this view of 3, I can actually subtract the 5. And what am I left with? Negative 2. So notice what we did. We actually modeled the start. We modeled the start. We prepared that start for being able to take away. or remove. Right? We modeled the start. That was 3. And then we said, yeah, that's 3 all right, but it's not the kind of 3 I want to see, because I need to see a 3 where I can actually remove 5. So we prepared it to make it look right, and then we did the taking away. So let's see what happens in another example. I'm going to go to our subtraction handout. So let's look at redrawing A and B, and then we'll move on to the other examples. So this was 3, and we're going to remove 2 of them. So we're going to be left with 1. This is a basic example from grade 1, maybe in kindergarten. Here we have 3, and we need to remove 5. So this is the change, and this is the start. Well, this start at 3 doesn't look like something where we can remove 5, so we're going to prepare it first. This is still 3, but this 3 is nice because I can remove 5. So the answer is going to be -2. So let's see what happens in C. If we prepare, this is start, we're going to remove, and this is change. The start is -3, and we need to remove -2. We need to remove -2. It's right there. So the answer is -1. Look at these 2 examples. These examples are some of the hardest operations to do, examples to do, calculations to do, when kids are following rules and procedures. They get confused with which sign you change, which sign you keep, do you add or do you subtract? What's the sign of the final answer? They get very, very confused. But if you allow them to base their thinking on visual models, then this becomes much more straightforward and much less reliant on memorization. So let's work on D. So again, we start with -3. We're going to remove -5. So it's modeled with -3. And we need to remove -5. At this point, this is not clear. We can't remove -5. But there's another way. We can write -3. This is another mat that's value of -3. But still we can't remove -5. Here's another mat, value of -3. And now I can remove -5. So the answer is +2. So we've modeled a number of different subtractions using integers. Is there much difference when we actually have to use polynomials? Well, let's do 5b minus 2b. This is our start. We're going to remove, and this is our change. So start is 5b. On the positive side. And we need to remove 2 b's. Visually, that's pretty straightforward. We're left with 3b. How about F? Actually, before I do F, I'd like you to pause this video and see if you can yourself model F, G, and H. And then you can play again. So let's try to look at G. Let's model G. We start, we remove, and that's the change. Let's say that's our P. That's our P, and we need to remove 4P. So we have 3P, we need to remove 4P. We don't have 4P to remove, but we can modify, we can prepare this mat by making it look a little bit different, but the value is still the same. The value is still 3p because all I've done is I've added a 0 pair. And now I can remove 4p. And what I'm left with is a p on the negative. Let's try h, start, remove, change. I'm going to start with negative 2x squared. Negative 2x squared. And I need to remove negative 5x squared. This is not I don't have negative 5x squared. But I can certainly add some 0 pairs of x squared. And that is enough. Because now I can take 5 from the negative side, and I'm going to be left with 3x squared. Notice again, we're not talking about combining like terms. We're not talking about keep, switch, change, or whatever that mnemonic is. We're not talking about adding the opposite. We're sticking with one particular definition and one particular model of subtraction, and that is removal. And we're able to explain all of these different situations from integers to polynomials using this removal process. But you're right, polynomials, you're probably thinking, but polynomials get a little bit harder than just that. Let's see how hard we can make them. So let's try pausing this video and working on I through L. And then when you're ready, you can press play again. Now we're going to go through K. This is our start. We're going to remove. This is our change. So the start is 3d squared on the positive and negative 4d. That's the start. And we need to be able to remove 5d squared plus 5. I need to be able to remove 5d squared plus 5. Now, this is not something I can do right now. I don't have 5d squareds on the positive side, and I don't have any singles at all. So let's prepare this mat using 0 pairs to be able to take that away. So I need to be able to have a couple of extra d squareds. Now I can take those away. But I'm not going to yet, because I also need to take away 5 units. So in order to be able to have them and to take away, I need to make sure that I've used 0 pairs to prepare the mat. And now I'm able to remove 5d squared and 5 from the positive. So what do I have? I have negative 4d, negative 2d squared, and negative 5. Again, notice that we've avoided all the complications about opening the parentheses with a negative sign, about combining like terms, about looking at whether the sign is the same or different, whether we're adding or subtracting the values of the coefficients. All of that is actually anchored on a visual representation, which has been consistent from all the way from adding and subtracting integers. So this means that we don't have to say to the student, wait, well, that worked then, but it's not going to work now. We've introduced them from the very beginning to something that is going to be a solid model all the way from the beginning to the end. And the final thing that I would like us to think about is, all right, so what happens when we run out of the ability to model specifically with Algeblocks? And I really don't think that anybody will be looking for 27x squareds and 32 x's, etc. That's just not reasonable to model or really to draw. So let's see what is actually happening here. Now, if we want to have, this is our start, we're going to remove, this is our change. Now, we are going to have negative 12x squared, but we need to be able to remove positive 15x squared. So we're going to add a zero pair, minus 15x squared and plus 15x squared. Then we'll be able to remove 15x squared. Now, if we have 15x and we need to remove negative 17x, we can do a zero pair, minus 17x plus 17x. And then we need to be able to remove 9. So we're going to have minus 9 plus 9. There's another zero pair. So let's see what it is that we're going to be removing. We're going to be removing 15x squared. We're going to be removing negative 17x, and we're going to be removing 9. All of those are going to go as we do this. That's going to be what is going to happen as we remove these values. So what we're going to be left with are this, this, and this. So let's see, minus 27x squared plus 15x plus 17x plus 32x minus 9. Do you see how the reasoning is absolutely valid and absolutely meaningful and possible, even when we're not actually drawing the Algeblocks? It extends. So the kids that are used to using Algeblocks, they can absolutely abstract from that and be able to use it for other more abstract examples. So that's the end of our subtraction. When we get back next week, we're going to be looking at why is it that subtracting is the same as adding the opposite, and how can we prove that? And then we'll move on to some other operations.